All right. Welcome, everyone. Good evening. I am Josh Schwartz, a second-year major here at Iowa State University in meteorology, and it is my pleasure to welcome you here tonight. We would like to thank the co-sponsors of tonight's lecture, the College of Liberal Arts and Sciences, the Department of the Earth, Atmosphere, and Climate, and the Committee on Lectures, which is funded by student government. Iowa State University, the Committee on Lectures, and the lecture program do not endorse the views of any guest speaker. A few housekeeping items. There will be an opportunity to ask the speaker questions. Please note that there is a microphone for you set up in the front in the center. Please do not use flash while taking photos. If you leave before the Q&A is finished, please exit quietly and refrain from talking until you have left the room. A lectures program student worker will be at the table near the doors to scan your student IDs if you are here for extra credit. Card scanning will not begin until the lecture is finished. All are welcome to stay for an open reception here in the Great Hall with refreshments as soon as the lecture is finished. Finally, I would like to briefly announce an upcoming event. On Monday, March 30th, internationally acclaimed bass baritone Simon Estes will join for the lecture, A Heart and a Voice. This special evening features the Iowa premiere of Simon Estes, A Heart and a Voice, a documentary highlighting Estes' groundbreaking opera career and humanitarian impact. The documentary will start at 5:30 here in the Great Hall, and following the screening, Estes will be joined in conversation by Brad Dell, the chair of the Department of Music and Theater, offering a rare opportunity to hear directly from the legendary artist. All lecture events are free and open to the public. A full schedule is available on the lectures program website. And now it is my pleasure to introduce Benjamin C. Withers, Dean of the College of Liberal Arts and Sciences, who leads the most academically diverse college at Iowa State University. The College of Liberal Arts and Sciences is cornerstone of nearly every major at Iowa State University, encompassing 21 academic departments, 1 professional school, more than 50 majors, and over 20 cross-disciplinary programs. Home to more than 6,000 students, LAS faculty teach over 40% of student credit hours here at the university. In his first year as dean, Dean Withers launched a college-wide strategic planning process focused on sustainable growth and led the creation of the Iowa State Center for Cyclone Civics, which advances nonpartisan civic education, free speech research, and efforts to strengthen civil literacy. Withers holds a master's degree and PhD in art history from the University of Chicago, specializing in early medieval manuscripts, and previously served in leadership roles at Colorado State University and the University of Kentucky. Please welcome Dean Withers to the stage.
So thank you, Josh, and thanks to all of you for filling the house today. Indeed, my introduction is not endorsed by the lecture series. Yes. It's my pleasure to be your host for the evening. This is the 40th lecture in this series, which highlights the faculty excellence in the College of Liberal Arts and Sciences. Each series, we focus on exceptional members of our faculty, and we invite them to present lectures from their own areas of scholarly expertise. They are faculty members who help solve global challenges, who connect the world with art and culture, and who push the boundaries of educational and intellectual dialogue. Over these 40 years, our topics have ranged from an examination of the history of separation chemistry and rare earth materials, to how we might improve the way we'll meet the next pandemic, and explorations of the ways that storytelling can connect communities and policymakers. So before I introduce tonight's speaker, I want to acknowledge the lectures program, thank them for their role in helping us sponsor and coordinate this event. I would also like to thank everyone from the LAS team who was involved in making tonight's lecture possible. The valuable partnership between lectures and LAS heightens our ability to share the college's contributions with the community and this is greatly appreciated. So, at this time, it is my pleasure to introduce Bill Gallus, Distinguished Professor in the Department of Earth, Atmosphere, and Climate. In his research, Bill uses multiple different weather prediction models to improve understanding and prediction of high-impact weather phenomena, especially thunderstorm systems with flood-producing rain, damaging winds, and tornadoes. Welcome to Iowa, right? Recently, he has begun to use artificial intelligence to improve the forecasts that come from traditional numerical models. Bill's lecture tonight will look back at the record-breaking derecho that traveled across Iowa on August 10th, 2020, currently the costliest thunderstorm event in the United States history. He will discuss why weather forecasts for the event were poor and reveal what research is being developed to help meteorologists improve future forecasts in extreme weather events. LAS research truly does transform the world by addressing challenging issues of our time, and Bill's work is no exception. He has served as chair of the National Science Foundation Graduate Research Fellowship Review Panel for Geosciences and received the National Weather Association Theodore Fujita Award for Research and Innovation. So please join me in welcoming the Spring LAS Distinguished Lecturer, Professor Bill Gallus.
Well, thank you, Dean Withers, and thank you all for coming out tonight. I just have to say this after the other intros that I'm pretty sure the lectures program does not endorse derechos, thankfully. So I'm going to be talking about this event from August 10, 2020, which I'm sure nobody remembers probably. No, this is one of those weather events that I'm pretty sure if you were hit by it, you remember it like it was yesterday, because you probably remember the winds were incredibly intense. They just didn't want to stop. And it was probably seemed a little surprising that it was happening in the first place because we didn't really get much advance warning. So the picture I have on this title slide is some damage to grain bins. This happened all over Iowa. This particular picture was from a town very close to Ames, from Luther, Iowa. Now, in addition to those things that I bet you all remember, one thing I remember being surprised by was how many Iowans were saying, "Is this a new thing? I've never heard of derecho before." And it's kind of funny because in the weather community, Iowa was already famous for derechos for two reasons. One, this was not a new phenomenon. Iowa had been hit by an extremely severe derecho on June 29th, 1998, which caused tremendous damage from the Des Moines area, the entire way along I-80 eastward into parts of Illinois. The other reason it's interesting that many people in Iowa didn't seem like they had ever heard of derecho before is the term was first used by Professor Gustavus Heinrichs. Now, he was at the wrong university, but at least it was here in Iowa in 1888, and he described a major wind event that crossed Iowa with a thunderstorm on July 31st, 1877. July 31st, August 10th. Those aren't too far apart. So both of these events were toward the end, the middle or end of the summer season. He chose the name derecho because in Spanish, it's an adjective that means straight, and he wanted to distinguish the winds in a derecho from those in a tornado where they are turning. So with the event we had in August, the winds were basically blowing in a straight line. Now, the National Weather Service has had a definition for derechos for a long time. Their definition says it's a widespread, long-lived, straight-line windstorm associated with a fast-moving complex of severe thunderstorms. So this radar image on the top of my figure is from the August 10 event. It starts once the system had already knocked out the power in Ames and was around Marshalltown. So you can see it is very large scale. It's racing rapidly across Iowa and Illinois. The bottom image are the storm reports from this particular event, where every little blue dot represents severe wind of 58 miles per hour or more. There's squares, black squares, that are hurricane-force gusts, and there are so many of them that in much of Iowa, they're canceling each other out, and it almost looks white. So we met the criteria clearly on the August 10th derecho. And there are actually specific rules to the size of the area that has to experience the severe wind before you can call something a derecho. The winds have to cause damage for at least 400 miles long. You have to have lots of reports of severe intensity, at least 58 miles per hour, and several well-separated hurricane-force wind gusts. If you think about this definition, there's one thing very strange about it meteorologically. No one can ever say they were hit by a derecho or that a derecho is rolling in. You have to wait until it's done, and you collect all the storm reports. Contrast that with you look out your window and you can't see your neighbor's house through the snow, and we Iowans know it's a blizzard because we also invented that word. You have to think about this. Is it really wise to live in Iowa where you invent the word derecho and the word blizzard? You see a tornado out your window, you know it's a tornado. So in this case, it's kind of odd, and there's a problem. To get those storm reports, you have to wait till people can get the information to the Weather Service, and when you have a very intense derecho, power is out. So it can take even longer than normal to know if what you were hit by was really a derecho. So traditionally, we meteorologists talk about two different kinds of derechos. One is known as a progressive derecho, and this is the kind that happens on a really hot, muggy summer day. It tends to happen by a weak front. So on the upper picture, here you see a stationary front. So usually there's not a lot of clues weather-wise that something is going to be able to start the thunderstorm. The other type of derecho, a serial derecho, tends to happen more throughout the entire year. And you get these when you have a really powerful weather system. So you have a big low pressure center, strong winds over a huge area. And with this kind of weather event, you might get several arcs of thunderstorms producing severe wind. So to drive home the point that we're really lucky to live in Iowa, Iowa was lucky enough to experience extreme examples of both types of derechos in just a 16-month period. So on the top again, the same radar loop, that's the August 10th derecho, which was a classic progressive derecho. Then 16 months later, on December 15 in 2021, we ended up having the first derecho ever documented in the entire United States in the month of December, here in Iowa, where it's normally a snow-covered wasteland in December. So both of these were high-end derechos of opposite types. Recently, there's been a change proposed in the definition of a derecho, which would help us to be able to maybe tell the people in Cedar Rapids, a derecho is rolling your way because it just hit us in Ames. So this effort is being led by scientists at the Storm Prediction Center in Norman, Oklahoma, and it's actually an Iowa State alum, Brian Squitieri, who is leading these efforts to change the definition. Most serial derechos, like the one we had in December, they happen on days where the winds in the atmosphere are already blowing incredibly strong. So all the thunderstorm has to do is, I joked in my class, it has to cough. It just has to do something to bring some of those really strong winds down to the ground. So that's really kind of like cheating. There's nothing special about the thunderstorm. So the new definition requires that the thunderstorms are doing most of the work to create the violent winds. And how we know that is happening is when the thunderstorms are racing along faster than the winds are blowing at any level in the atmosphere. So it's not like you dropping a leaf in a stream and it just floats down. The thunderstorm is doing something to the atmosphere so that it can move extremely quickly. And a good example is our August 10th derecho. So weather balloons in Iowa in the summer are typically launched just at 7 in the morning and 7 in the evening. But on August 10th, the Davenport National Weather Service office knew something bad was headed their way, so they launched a weather balloon at noon. And this weather balloon showed you could go up almost 5 miles in the atmosphere, and the winds were never stronger than 35 miles per hour. Well, the derecho was moving at 60 to 70, almost twice that speed across Iowa, and producing winds reaching 140 miles per hour. So the August 10th derecho would clearly remain classified as a derecho with this new definition, but in the future, it's likely that only progressive derechos will still be considered derechos. So now that you know what a derecho is, that it actually has a fairly long history, the word being used, we can ask, well, how do derechos form? Well, a derecho is a type of thunderstorm, so we can think about, well, what are the ingredients for a thunderstorm? One is something we meteorologists call instability. So that happens when it's very warm and humid down low in the atmosphere, and it's much colder up high. So if something can give a little shove upward to the air finds itself warmer than the air around it. So it's positively buoyant. It acts like a hot air balloon. So it's just going to take off rising on its own. And if the second ingredient is present, moisture, you can see this because you'll see the cotton ball type clouds that are growing taller and taller with time because you have the instability being released in the atmosphere. You have this hot air balloon effect taking place. Now, moisture, the second ingredient, is a very interesting ingredient. You may not be aware of this, but when the water in our atmosphere is in the gas phase, and we call it water vapor, and it's invisible, when it changes into liquid water, which we see as clouds, it releases heat. So I sometimes joke, you're walking around all the time in an atmosphere that's full of dynamite, okay? So moisture is important to get a thunderstorm because once you start creating the cloud, it's like you're stoking the fire in your hot air balloon. You're giving off all this extra heat, which will help your cloud to build higher and higher. And then finally, I already alluded to this, you need something in the beginning to give a little push upward to the air. Usually that is a front, a cold front, a warm front, or a stationary front. So this schematic shows when you have cold air rolling in, it's heavier than warm air, so it's going to be pushing the warm air out ahead of it upward. And that can be the trigger that sets all those ingredients into motion and gives us our thunderstorm. Well, a normal thunderstorm does not live very long, and I'm going to show you why. So there has to be some other ingredient that we add to the mix to get a long-lived, powerful thunderstorm that can become a derecho. And that ingredient is something known as wind shear, just a change in the wind direction or a change in the wind speed as you go up through the atmosphere. So if you don't have wind shear, as you play with those ingredients, you first get the air is rising. The hot air balloon effect is taking place on the left. Then once you've had your cloud be around long enough, some of the droplets, they're banging together, some of the droplets get big enough to start to fall out as rain. Well, the falling rain helps drag the air downward, and some of the water evaporates, which cools the air. That acts like a swamp cooler, and cold air is heavy. So that air is going to want to sink. If you have no wind shear, the air that's trying to sink is going to be trying to sink in exactly the same spot where you're wanting your hot air balloon to be rising. So within about 20 to 30 minutes, a thunderstorm will die if there is no wind shear. If you add wind shear into the mix, it helps organize the storm. So the rain and the sinking air, which is shown with the blue arrows, ends up in one part of the thunderstorm, and the air that's rising, making use of the instability, kind of the hot air balloon effect, is happening on another part of the storm, usually the front side of the storm. So it can last a long time. This is a picture I took on a storm chase in western Nebraska as a graduate student. So this demonstrates some of these concepts. The air is rising in the middle portion where it looks like a giant's boot coming down from the sky. You always know where air is rising in the atmosphere if you can see the clouds very crisply, see the detailed structure. That is a sign the air is rising. Contrast that to the right side of the picture where everything becomes kind of a fuzzy gray. That is where the rain is falling, the air is sinking. And so on this day, I know there is wind shear, which I've indicated with a yellow arrow, because something is causing all the water to fall out on the one side of the storm and to not interfere with the area of upward motion where a tornado was about to touch down. So you know the ingredients now for a long-lived thunderstorm. What do you do differently to get a derecho? And this is something we're still learning about, but it appears one key ingredient, you need your hot air balloon to be on steroids. Okay, you need very unstable atmosphere because this allows for strong thunderstorms that can produce an incredible amount of snow and hail in the clouds, which melts into rain. And you need the second bullet. You need a layer of dry air, which can actually be pretty thin, that will cause all of that falling rain to suddenly want to evaporate when it passes through the dry layer. So now you have a swamp cooler on steroids, so to speak. This cold, heavy air will rapidly plunge to the ground, accelerate, and lead to very strong winds at the surface. And you still need, the third bullet, you still need something to trigger, to lift the air in the first place. And here's where Mother Nature doesn't play fairly, that the environments that give us the first two bullets are generally the environments where there's almost no clue that something is going to be able to lift the air. It becomes very difficult to see, well, what could actually trigger the thunderstorm? So that makes forecasting difficult. So if we look back at the details of the August 10th derecho, the upper left image was created by several of the local National Weather Service offices, and I've labeled Ames, Des Moines, and Cedar Rapids so you can get an idea of the scale of the winds. The light blue color would be winds estimated to be at least 80 miles per hour. So Ames was impacted by this for the most part. A huge chunk of the state had winds that strong, and there's yellow showing up by Cedar Rapids, where the winds were estimated over 120 miles per hour. If you lived in an urban area in Iowa, where we typically have a lot of trees, you saw scenes like the upper right, which was taken in Des Moines. If you lived in rural areas, you saw scenes like the lower left, which was the main contributor to the $12 billion in damage that was done. Cornfields were completely flattened, and in fact, aliens could tell that the cornfields were flattened because the lower right is a satellite called Sentinel satellite, where we can monitor what's happening at the ground. Before the derecho, all of Iowa is in this dark green color. After the derecho, the area outlined in yellow, and it's kind of hard to see with the projector here, but it actually becomes more yellow in color, which was a sign that the corn was actually crushed down to the ground by the intense winds over that huge swath of our state. So the August 10th derecho was possibly as intense as a derecho can get. It set a record in Iowa for the strongest wind ever measured by an instrument, 126 miles per hour. Ironically, look at the record that it beat. That was set in the 1998 derecho. And the Weather Service estimated, based on damage, that the winds around Cedar Rapids were as high as 140 to 145 miles per hour, which is comparable to a Category 4 hurricane. And perhaps the most amazing aspect of our derecho was the duration of the wind. It just didn't want to stop. One instrument in eastern Iowa had winds above the severe level for over an hour straight, which I think is why a lot of media outlets started to call this an inland hurricane, because the behavior of the wind was a lot more like a hurricane than our typical thunderstorms. So the combination of such strong winds over such a long time period is what led to the incredible amount of damage. And as we said earlier, 12 billion. So it's still the costliest single thunderstorm event in US history. So you would hope with such a high-end weather event that we all would have had a lot of time to get ready for it. I mean, if you live on the coast, typically you might have 7 days where you know a hurricane is out in the ocean heading your direction. So maybe you could, if you're an optimist, you could say, well, I'm happy I didn't have 7 days to worry about it coming. But most people want a little bit of advance notice. So the official forecasts for severe weather come from a branch of NOAA called the Storm Prediction Center. They did not highlight central Iowa for much risk of storms until about 2 to 3 hours before it hit. So upper left, this is a routine product they issue. This is the probability that you will have severe thunderstorm winds. This is midday on August 9th. Only 20 hours beforehand, most of central Iowa is white, meaning basically there's no chance. While we're sleeping the night before in the upper right, their next update came in. So 12:30 in the morning, 8 hours before the derecho was organizing in western Iowa, they slightly tweaked the little brown area of a 5% chance to include some of central Iowa. When you were waking up in the morning, an hour before it was hitting, they had finally raised the probabilities. We're in this yellow zone in most of Iowa, which is a 15 to 30% chance. It really wasn't until Ames lost power at 11 a.m. that they finally upgraded and let people know downstream, you're going to be in for something bad. Well, there's a reason for why the official forecasts were poor. When we all went to bed the night before, this is what our 4 best computer forecasting models showed would be happening at 1 in the afternoon on August 10th. In meteorology, we rely very heavily on these sophisticated computer programs that can have 100,000 plus lines of code. Unlike some fields where they take a lot of data and they just grab a math equation that fits the data well, we start with the actual laws of physics. So our challenge is simply, well, how do you go from the laws of physics and code it up to work well in a computer? And normally the models do a pretty good job. Well, in this case, upper left, go for a picnic. You're gonna have a beautiful day in Iowa. Upper right, go for a picnic. There might be some sprinkles down by I-80, but nothing bad. Lower left, have a happy day. It's going to be beautiful in Iowa. And in the lower right, well, be glad you're not in Illinois or Missouri. They might have some thunderstorms, but hey, Iowa is going to be fine. So we all went to bed. This is what we were seeing. Instead, at 1 p.m. on August 10th, this is what the radar actually looked like. A very intense line of storms with a backward C shape in eastern Iowa. Much of the state is within the solid yellow line here, which is a severe thunderstorm watch. And actually, in a lot of Iowa, it was a very rare, particularly dangerous situation watch because they were expecting winds could be hitting 80 to 100 miles per hour. And if you looked at the radar images 1 hour apart, this is what you would see starting at 8 a.m. in Nebraska, ending at 7 p.m. near the Ohio-Indiana border. The system was really moving. Even if you were on I-80, you would have probably had a very difficult time staying ahead of this as it was moving around 70 miles per hour. So one of the things I think that really amazed the weather community internationally were the videos that came out of Cedar Rapids, because it really showed how long the winds just maintained this ferocious intensity. So my favorite is this short 2-minute clip that was filmed at the country club in Cedar Rapids. So I want to play this for you, and I want you just to note how the wind just keeps coming in wave after wave. So as you watch this, you probably have watched powerful storms roll in, and we're used to maybe the first minute or two, you get the really strong winds. If you lose a tree branch, that's when it happens. So here the winds are starting to ramp up. We lost a branch. We lost the top half of the tree. The visibility drops to blizzard level just from the rain being blown. And so just from this country club, it probably wouldn't surprise you to know that in Cedar Rapids, they lost 2/3 of their entire tree canopy. So remember, all the computer models said you should be outside having a picnic right now. Here, right about the time you'd think things are going to start to calm down, but it seems to me the very strongest winds actually are happening at the end of the clip. So my research team at Iowa State then, shortly after the derecho, decided to try to take a look at it, figure out why were the forecasts so bad, why did the winds last so long, and why were they so strong? And so I was able to do a visit about 2 years after the derecho to the National Center for Atmospheric Research and play with a brand new model known as the FV3. It was supposed to become the ring that rules them all, the new weather model that we would run for every application we had. So this is a kind of complicated figure, but what we found in the study is really fascinating. So I'm showing you on the left side, it says 25 kilometers. Okay, if you want to run a computer model over the entire planet or run it for a long time, like for a climate simulation, that's very expensive computationally. So you keep your grid points where you're doing your calculations pretty far apart. So 25 kilometers, It's about 15 miles apart. In the middle, 13, kind of the Goldilocks zone, is about 8 miles apart. On the right are the state-of-the-art models that we run, where the grid points are about 2 miles apart. So this is what we tend to use nowadays to forecast thunderstorms. The top row of plots here are from me running the model, where I am not using a separate little piece of code that's almost like a cheat sheet that helps the model show thunderstorms. Because when your grid points are 15 miles apart, and you think about how big is a normal thunderstorm, you might have friends in West Ames. Oh, it's pouring at our house, and you're in East Ames. The sun is shining here. So thunderstorms are small. So on coarse grids, you need help usually. The bottom row shows if you actually turn on the special code. So among the things we found, when you're running with the grid points really far apart, the top figure should be terrible. You really are supposed to need this cheat sheet thunderstorm code to work. But this is all valid at 1 p.m. on the day of the derecho, and the model run started at 7 p.m. the night before. I would say that is an impressive forecast for such a coarse model. There's a big ugly red smear in the middle of Iowa. That can't be good if you're talking about weather. However, if you turn on the thunderstorm code that's supposed to help you in the bottom, you actually get a worse forecast. So that is very puzzling. I'm not going to explain. We did figure out why that's going on. In the middle, it's the Goldilocks zone. Not much changes. We get to the right. So the upper right, that is how we run our 3 kilometer, our 2 mile models. We don't need the cheat sheet because 2 miles is really close together. So all the forecasts we had looked pretty bad. In this case, yeah, there's a lot of thunderstorms in Illinois rolling into Indiana at 1 p.m., but in Iowa, it doesn't look too bad in that run. If I turn on the cheat sheet, which every meteorologist knows you do not need to run that on the fine model, so in the lower right, what's going on here? When I turn on the cheat sheet, now I actually have a really good simulation of the derecho. So what is happening? How can this be? So the top row in this picture is what radar was actually seeing. And so if you remember this day, you probably remember we all slept very nicely the night before, that we were not interrupted by storms. And we see at 4 in the morning, 7 in the morning, there's really nothing going on in Iowa. At 10 in the morning, yes, here in Ames it was getting a little scary. There was a very nasty line of storms coming toward us from the west. And by 1 p.m. is when Cedar Rapids was really under the gun for the severe weather. The middle row here is what is happening in my state-of-the-art model when I am not using the cheat sheet. And now we can see what's going wrong. This model at 4 a.m. and 7 a.m. has a big thunderstorm system rolling through Iowa. So we would have all woken up very grumpy on August 10th because our sleep would have been interrupted by storms. But as the day went on, we would have had a nice day. We would have never had the derecho. So that's what most of our models were telling us. When you turn on the cheat sheet, which is really just supposed to help you get storms, on the left side in the bottom, there's a lot less stuff happening at 4 in the morning. 7 in the morning, again, there's very little happening in Iowa. We've cleaned up all the fake storms by doing this so that by 10 in the morning, the third panel over on the bottom, that looks pretty close to reality with a line of storms rolling toward Ames. And in the lower right, that looks like an impressive derecho at 1 in the morning. So the normal way of running our state-of-the-art models, where we don't use the cheat sheet, gives us fictitious storms the night before the derecho that uses up all the instability. So the derecho could not happen. So the left panel, this is observations. This is really what it looked like at 10 in the morning, about an hour before the derecho hit Ames. And those red lines are showing values of a quantity that we call CAPE. It's a measure of instability. There was a lot of instability. The models, the way we normally run them, in the middle, all of this white color. There's no instability left because the nighttime storms used it all up. But when we turned on the cheat sheet and stopped the fake storms, we have the lower right picture, lots of color over Iowa, lots of instability, which is very much like what was really happening. So the craziest thing of all, in my opinion, is how does this thunderstorm cheat sheet stop fictitious storms? That's not its job. Its job is to help give you thunderstorms. So this is a kind of plot we use a lot in meteorology called a sounding. We plot temperature, which are the lines on the right, the solid lines, and we plot moisture or dew point with dashed lines on the left. In this picture, the red lines is what happened when I ran the model and I actually had this thunderstorm cheat sheet turned on. The blue lines is when I didn't use it. Blue, of course, is what we normally would do with such a state-of-the-art model. Very little difference. However, if you look at where the black arrow is pointing, when you have the thunderstorm cheat sheet on, it's looking at the profiles, and it decides, and this is at 11 p.m., the day before the derecho, oh, I think the atmosphere, there's some cumulus clouds would want to form. And that would cause the air to mix up a little bit. So I get this tiny little bulge of warming. So there's about a degree or two of warming and a bit of drying and a layer that's only 1,500 feet thick. That acts like putting a lid on a boiling pot of water, and that was enough to stop all the fictitious storms from forming the night before, which gave us a good forecast of the derecho. In fact, how good is the forecast? I plotted the temperature prediction in the model at noon. And this map is in degrees Celsius, but the green colors that you see to the right of the blue are temperatures around 85 degrees before the storm hits. The dark blues and purples are in the 50s. Well, does anybody here remember going outside to look at the aftermath of the storm, like as soon as you could, as soon as the winds died? I went to my front door to look at my thermometer, and I'm used to, in really strong storms, I see the temperature might drop to like the upper 60s. I did a literal double take. I walked away and thought, wait, I think it was the upper 50s. And so I went back and looked and saw it was the upper 50s. And then smartly, I proceeded to walk out the front door, not thinking about what it meant that it was only 58 degrees. I instantly turned around, went back in and grabbed a jacket. So it was incredibly cold from the amount of evaporation and the cooling that did in this particular derecho. This model run also showed a peak wind of 94 miles per hour. So getting rid of the fake storms would have allowed us to have an actually pretty good prediction of what might happen on Monday, August 10th. Now, more recently, I had a master's student, Nick Marcus, who's here, use a tried and true model that's been around for 25 years, known as the WRF, the Weather, Research, and Forecasting Model. He found, even if he went down and had the grid points 1 kilometer apart, which is like 2/3 of a mile apart, he ran into the same problem. Fictitious storms formed the night before, and to get rid of them, he had to turn on one of these thunderstorm cheat sheets. In this case, he had to turn on a different one than what worked in the other model. And the other thing that was a little odd, in this model, the problem wasn't so much that the whole state of Iowa had big fictitious storms rolling through the night before. It was there were a few storms, but because the atmosphere had that important dry layer, those few storms were bringing the dry air down to the ground where the winds were spreading it out, and so that you were ruining the instability. There was no energy for the storm, so you ran into the same problem. So when Nick turned on the thunderstorm cheat sheet, he produced the image in the lower left of what the model prediction would have showed radar looking like every hour, and I'm comparing that to the actual radar for what really happened. I feel very fortunate as I'm getting older in my career that I can be a scientist who says, I actually had a moment where I got goosebumps from the results. I was like, oh my goodness, this is like we had a crystal ball that could see exactly the terrible things that were going to happen 18 hours later. So the simulation was very good by doing this. This plot in color shows, well, how long in the model were the winds blowing with severe intensity. There's some orange and red colors, getting up to 33 straight minutes of winds howling at over 58 miles an hour. Now, as I pointed out, in the real world, we actually had a place or two that had 60 minutes. So this isn't perfect, but that is still an incredibly long period in a thunderstorm to have strong winds, and the winds were getting up to 132 miles per hour in his model simulation. And if you looked at how wind was changing over time in the area where the strong winds lasted long, you saw behavior that was very much like what you saw in that video clip from the country club. Wave after wave of really strong wind sort of superimposed on a background that already was really strong. So we felt that this simulation was representing reality so well, we could maybe learn a little bit about why the winds were so strong and why they lasted so long. So one of the things he did is he took these slices every 30 minutes from about 11:30 in the morning until 2 in the afternoon. And I tried to highlight the colors are the speed of the wind. When you're getting into the purples, we're talking 100-mile-an-hour winds. So on one of the images, I put a yellow arrow. We discovered this system ended up with a river of air. This is known as a rear inflow jet. So this river of air comes in the back of the storm, the west side of the storm, and it's gradually sinking with very strong winds to the ground. And it's very extensive in the derecho, which means that when it was reaching the ground, you would have a long period of intense wind. In addition, when the system got closer to Cedar Rapids, we plotted up a field of pressure, which is what the black lines are showing, and found you actually developed a vortex. You develop a low pressure center. The air goes around the low pressure center counterclockwise. That accelerates it. That leads to even stronger winds. So the light pink and the dark pink contour are places where the winds are blowing at 75 and 100 miles per hour. So radar in this event was showing this swirling happening as the system got near Cedar Rapids. So we think the Model 1 actually also correctly indicated that that was the icing on the terrible cake that rolled into eastern Iowa and made the winds even worse there. We also found the strongest winds happen when it's raining the hardest in the model. So the bluish colors here are referring to values of radar reflectivity, like how intense is the rain. If you're used to looking at radar on the TV weather or on an app, this would be the red stuff, okay, the really powerful rain. And the pink and dark pink contours, again, are the strongest winds. And at almost every time, there's this match. So this is pretty good evidence that it's the evaporation of the falling rain that is leading to the very, very strong winds, like the peak winds. And this is happening when the system is moving into a part of eastern Iowa where I'm showing a sounding again. So there's a temperature curve and a moisture curve. Where the red and green lines go apart about a mile or two above the ground, that is very low relative humidity. That is dry air. So you're sending this intense thunderstorm full of heavy snow and hail up in the cloud, heavy rain down below, into an environment where there's this dry layer that can evaporate a lot of it, making the air very cold. So finally, during fall, I was able to do a sabbatical, and I spent some time back at the National Center for Atmospheric Research to work with the very newest model because they decided, well, this FV3 isn't as good as we thought it would be, but for sure, this model, the MPAS, becomes the ring to rule them all. It will replace all the models that NOAA runs in late 2027 or early 2028. You would hope our brand new model that we're going to switch everything to maybe solves the problem. It doesn't need help from this little thunderstorm cheat sheet. No, it does. So on the left, the normal way we run the model, and you can see the upper left, 7 in the morning, we're all crabby in Iowa because we were woken up by thunderstorms all night long, which isn't what happened. And at 1 in the afternoon, the model would say we're all having a picnic, it's a beautiful day, which again is not what happened. You turn on the specific thunderstorm cheat sheet on the right. Now at 7 in the morning, there's just a little bit of rain. We avoided the fake nighttime storms, so we actually do have some heavy thunderstorms rolling through central Iowa at the right time. So to wrap this up, to summarize, the 10th August 2020 derecho was among the most intense ever observed. It was poorly forecast, like a surprisingly large number of derechos. The generation of such an intense system requires the perfect mix of ingredients that can be difficult for us to detect ahead of time. So one thing I've noticed is most Iowans after this derecho, if they hear the word derecho, they think August 10. You should realize there's a spectrum, and that was the extreme end. So hopefully none of us will ever see that intensity again, but even a regular strength derecho is an event that you'd want to take shelter from. So what does the future hold? Well, because the 2020 derecho was so much more powerful than a normal severe thunderstorm, the National Weather Service made changes so that high-end severe thunderstorm warnings now activate your cell phones. They didn't back then. Only tornado warnings would make your phone buzz. Now, thanks to our derecho, your phones will ring. I think if the National Weather Service mentions 70 or it might be 80 miles an hour as the wind. In addition, I believe forecasters are more aware that model predictions might be bad if they actually don't do a good job at the start. And they are maybe paying more attention to low probability scenarios. So you could say, well, 1 out of 10 forecasts said that August 10th would have a bad storm happen. You might be inclined to say it's only a 10% chance. I'm not going to trust it. But I think now we know, well, that might actually be right, and we need to pay more attention to the details. What's happening now? What were the different models saying would be happening now? Finally, I think every media interview that I was asked to give right after the derecho, a reporter asked me, is this related to climate change? Is climate change making derechos worse? Nobody had really done research yet in 2020, so we have started to do some research here at Iowa State. So Josh, who introduced the dean earlier, is working on a project with a colleague of mine, Dr. Cristina Patricola di Rosario. He has run 36 model simulations using something called the storyline approach. So you take climate model prediction data. In our case, we're only going out about 30 years. Okay, so how would the 2020 derecho be different if it happened in 2050? So you use the climate model data on how the atmosphere is changing to alter the background slightly, but then you give it the exact same weather conditions that happened on August 10th, and you see, well, how would things be different? So we chose to do 36 simulations to give us an idea of the certainty or the uncertainty. You don't want to just hit the Powerball jackpot. You did one and it just happened to show you something when like 99 other ones, if you had done them, would have said the opposite. So you can trust the results more when you do a lot of runs. So in white, this shows what happened with the 2020 derecho. The colors are what happens in the future when you use these 5 different climate model, they're called deltas, or changes that take place. So I have 4 different measures of how bad the derecho is. So the upper left would be the area where severe winds last for more than 10 minutes. And comparing the white box and whisker plots to the other ones, most of the time, yeah, the area gets bigger in 2050. Upper right, just the area in general where people have severe intensity wind. Yeah, for the most part, it looks like a bigger area is affected in the future. In the lower panels, I had him look at an area about the size of an Iowa county. So the lower left is really what is the average wind speed in the worst hit Iowa county? It goes up a lot in most of the model runs. And what is the length of time of having severe winds in the worst hit county? In the lower right, that also goes up. There's one climate model, however, that says, you don't want to maybe bet the farm on this. There's a little bit of uncertainty. The one in purple is the one that suggests, well, maybe things won't be worse. But this suggests to us there is some uncertainty, but overall, sadly, it looks like with the kind of changes that have been taking place in the climate, a derecho like this one would actually be a bit worse in 2050. So with that, I thank you for coming tonight, and I will answer any questions that you might have.
Thank you, Bill. That was wonderful.
Thank you.
I'd like to acknowledge some special guests that we have here tonight, President and Dr. Cook. Thank you for enjoying this lecture with us. So we do have a few moments for questions, and we have some microphones here if you've got a question for Dr. Gallus. Looks like we got some brave people coming forward. Thank you.
Yeah, sure. I'll take the first question. So you mentioned that you implicated this like weak little cumulus field as sort of being the responsible factor causing that slight warming, that slight drying, that completely changed the whole outcome of the event. But earlier on, you had mentioned that like one of your subtle triggers tends to be these like tends to be more related to lift. And so I was just wondering, like it seemed to be like almost a symptom of what the primary trigger would be. So were you able to identify like some of these subtle lift triggers as differences between the models that ultimately led to this weak cumulus field, and then that got the ball rolling?
So we were we were finding there was weak lift in this event because a cold front had come through, and there was something else going on where the winds were converging a little bit above the ground. So in our case, I don't want to imply that in reality a cumulus field developed and put the warm layer. In the model, that was necessary to stop the fake storms. But you have to realize, so the Weather Service sends up weather balloons just twice a day. The closest ones to central Iowa, there's one in Omaha, there's one in Davenport, one in Minneapolis, and one in Topeka. So I think the bigger issue is we just don't have the resolution of the data that we would need. So it's quite possible we were missing information that would have shown there actually was a little bit more warming than the models had when they started running for this event. But it could have, I didn't look at the satellite. Visible satellite doesn't work at night, and this was at 11 p.m. So it could have been something like this was happening too. I think the main issue was you needed that tiny change in the temperature profile, which honestly, I found that scary. I thought the difference between getting nothing and a $12 billion disaster is that's kind of sad to think about, actually. But it implies if there's ever a chance to get more weather instruments, I don't know if the general public realizes this, how much weather forecasting would be helped if there was a better network, better ways to gather data over more points.
So it's not actually known if that that cumulus field actually materialized in reality.
There were a few weak showers that developed. So I think the radar is suggestive that some weak things like the cumulus field were going on that night. But I didn't explore that in more detail. I was just more happy to be able to attribute why in the model run are we able to stop the fictitious storms and then get the really good simulation of the derecho.
That's really interesting. Thank you.
This is maybe a selfish question. I've been wondering for 50 years if you could tell me what it was I experienced in 1968. I was clearing out limbs from my grandpa's grove, and I got out by the west fence one time, and here was this black, thin cloud just rolling towards us, very low to the ground. I didn't know what it was, but I said, let's get in cover. We took cover in a hog house. I don't think that was a good place. But when I came out, maple trees that would take 2 or 3 of us to be around were all broken down. My limb dragging ended with that. But what was it that I experienced?
So when you mentioned 68, I was going to say, do you know by any chance, was it mid-May? 68 is famous in Iowa because it was 2 F5 tornadoes on the same day, the Charles City and Olwine tornadoes. So, but what you were describing actually sounds like a type of cloud called a roll cloud that often is produced by storms that have strong wind. So I actually was doing my usual thing for the August 10th derecho. I went out in the front porch to watch it. And based on radar, I thought, oh, this is going to be really pretty. It was ugly. And it didn't have the normal, for having such impressive winds, it really failed in the photogenic department as far as I could say. But it is possible that the event you saw was one of these roll clouds, and it was what we might think of as downburst or microburst winds, very strong straight line winds.
That's what I've always suspected. Thank you.
Hi, I too would like you to explain what happened to me. It's not the same as his, but they were calling what I experienced a derecho, but then according to your definitions now, it probably wasn't a derecho, but it happened about that same time. I was working a job. I was going to get off in the early afternoon. People at work who were able to keep track of the weather forecast said it wasn't going to hit our area for a couple hours. So I says, well, okay, I'll stop and grab some food. In case electricity goes out, I'll have some food. So I stopped at a close-by restaurant, and they had some TVs on, and they were showing the line of thunderstorms were far, I live in northwest, north central kind of Iowa area. They were showing them clear over into Ida County. About 3 minutes after I left the restaurant, small raindrops started coming down, and about 3 minutes later, it just came down like crazy. The wind was blowing so hard that it was going sideways, the rain was. I could hardly see. It was like a blizzard, and I was driving to my place, which I should have been able to make it, and within 20 minutes after leaving the restaurant, and I just kept driving because I was out in the middle of nowhere, and it just kept raining and the winds were blowing so hard. Then I went through this one small town, and shortly after that, it was calm. But all kinds of power lines were down, tree limbs were down. They said a neighbor of mine had a tornado go through there. Plus, was this just a really extreme, strong thunderstorm? And why was it at least an hour before it hit my place? Why was it so much quicker to arrive than what they were predicting?
So the event you describe again sounds like a microburst or a downburst. Depends on how big an area was hit by those winds, but with describing the rain and the wind coming outward. For the forecast, if this was in 68, forecast, whether you believe this or not, we have lots of statistics that show forecasts have greatly improved over time. So I don't know what, if the forecast was just, might have been rather poor, or it could have been a new, sometimes when you have thunderstorms, existing cells, they're sending out their cool air, and it forces the air ahead of them to rise, and new thunderstorms can form. And it's possible that, you watch something that said this storm is moving in, but as it was moving in, a new storm blew up in front of it, so that would have hit you before you would have expected to be hit by the original. In fact, that happened to me last summer on a day where Ames got like 4.5 inches of rain in 2 hours. It started to storm much faster than I expected, and I looked, and it was because a new storm had blown up just in front of the one I was tracking.
Well, I would have stayed at the restaurant if I had known it was going to come out faster.
Okay, so yeah, we'll take 3 more, and then at the reception, I'll be hanging around. If you didn't get to ask your question, I'll gladly answer questions then. Hi, Ann.
Hi, Bill. So I had not heard of a derecho until 2012, and it came across Chicago and went through northern Indiana. We have a family farm there with woods, and it looked like a bomb hit. So did you study that? So that was June 30th, July 1, 2012. Did you study that? Anything different about that?
So that's was the most famous derecho for sure until the Iowa one happened, because that one moved the entire way across the Appalachians, hit Washington, D.C. At 10 o'clock or so at night, knocked out power for millions of people in a heat wave where it was like over 100 degrees day after day. So it got a lot of attention. I think we actually looked at that because we were trying to identify cases of especially strong winds and especially long duration.
So it went from Chicago all
Yes.
the way?
And it went off the East Coast, actually.
Wow.
So I believe the issue we ran into that one is even though it had very strong winds and affected a big area, I don't think we couldn't find stations where the winds stayed severe for long enough period. We wanted like 20 minutes of strong winds the way the Iowa derecho behaved. I believe that was the issue on, in fact, I'm looking at my 2 students. Oh, and there were no winds that reached 100. Yeah, our bar was set high. I mean, we're Iowans. I mean, look what we went through that. So it's not a derecho unless it's 100+ mile per hour winds. So.
Yeah, we were supposed to be camping in those woods that weekend. We decided to do it the next weekend instead. We probably all would have been killed because the woods, the trees just collapsed on the camping ground. Yeah.
Right. Yeah, I always think personally the most amazing thing about the August derecho in Iowa is that there were only 4 deaths.
Yeah.
In the meteorology community, Iowans are known as being really weather savvy, and I think that event proved it. Hi, Alexis.
Hello. Yes, after this event, we found on the Weather Service side of things, there's a very big reference when we start using the word derecho, because people usually, as you mentioned, think back to this day. So you had mentioned in your talk about the idea of messaging that term ahead of time rather than a post-storm analysis. And I'm curious in your thoughts on how to, I guess, maintain that reverence without crying wolf too much in a low confidence but high impact scenario like that.
So I think that so Brian, my former student who coined the term, is actually coming here to Iowa tomorrow to give a talk. So I think one of the issues that gets confusing is, are you still going to keep the rules on aerial coverage? Because then if you tell somebody a derecho's coming, you could easily be wrong. If you simply mean a storm with very powerful winds because you can see it's moving a lot faster than the winds in the atmosphere, then you're not going to be wrong so much, but the connotation that people have, it could look wrong. So it is always tricky when you figure out how do you best, train people or get people aware of changes that we might make in our terminology so that they have the best information to base their decisions on to stay safe. So that's probably something that will need some work looking at that in these next few years now that the definition's changing.
Thank you, Dr. Gallas, for a very interesting talk. My question is about climate change. At the end, you showed some interesting data. If I'm not mistaken, climate change, that is the human-caused portion of climate change, seems to come from various factors, not just one factor. So greenhouse gases and various things. Is there any way you can tell what part of climate change might contribute to that data you were presenting? What specific things that human activity creates that might have contributed to that data?
We didn't do that. So we looked at, in fact, Josh, I don't remember how many. We looked at a range of different climate models. And we actually, the 5 we selected, it was to give a good variety in what they showed the central United States, the impact on temperature and moisture with time. It would be the people that actually run those models would have the ability, I think, to be able to go in to try to discern what fraction of the CO2 increase is due to this versus that. So yeah, we didn't look at that. Ours is just more the standpoint of if a derecho happens with a climate that's continuing to warm and get more moist, which typically means more instability, how might it affect derechos?
Right. So for whatever factor contributes to that, it could be one of many or several. Thank you.
Thanks again, Bill. So once again, let's thank Dr. Gallas. As Bill mentioned earlier, we do have a reception. I invite you all to stay for a bit, ask some more weather questions, and share your weather experiences with Bill. I'd be certainly interested in hearing more of those. He'll be available for a short time for those questions. I'd also like to highlight that we have some future events coming up in the college. This week in particular is LAS Week on campus. We have 30 some odd events that focus on our students and our faculty at work. Please join us. And if you have the opportunity, look at our LAS website and you can find those list of events there. So thank you for being a wonderful audience. Once again, let's thank Bill and have a good evening.
I never get tired of listening to weather stories.
I'm glad that people ask questions. Mine was going to be embarrassing. When I was looking at those 1 hour radars, I'm a medievalist, right? I'm used to looking at medieval manuscripts. That kept reminding me of letters. I was trying to find the hidden meaning. There's an S and an S. Is that Mississippi?
Interesting. We should bring you in and have you look more closely. Maybe the model's trying to tell us.
Yeah, that's right. Nature's graffiti.
Yeah, right.
Wouldn't that be an interesting?